So in this particular section, we talk about now light in general, what light is going to be. So let's look at something called polarization. Okay, so what is polarization? So polarization is, for example, let's take a look at this. Yeah, forgive my drawing. So this is Y, X, Z. All right. So this is an electromagnetic wave example. This is the electric field. I mean, this is symmetrical actually. It does not come out in that way in my drawing. So, okay, so this is like the plane of oscillation. This is of the electric field, E. Okay, there is obviously the magnetic field as well, which let me represent it like this. That. So that is B, a magnetic field, and this is the electric field. Okay, so if you look at this particular situation, you will see that, this is Z, Y, and so the electric field is something like this, back to E. All right, so this is like the plane of oscillation. The plane, so this particular says that the plane containing the E vectors is called the plane of oscillation or vibration. The plane of oscillation or vibration. Right. Okay, so we represent the wave's polarization by showing the extent of its electric field oscillations in a head-on view. So this is the head-on view. Okay, so this shows the wave's polarization, okay, by head-on view of the plane of oscillation. Okay, so this is the head-on view which represents the wave's polarization. Right? The wave's polarization. So that is what is represented in this particular view. All right. So we know that what we are doing therefore. Okay. So now that let us consider two orthogonal components. Okay, two orthogonal components, two orthogonal optical disturbances. Okay, so one is say EX. Both are propagating in the Z direction, remember. This is I, E0X cos AX omega T, right? The other one, if you look at it, is given as EY ZT, given as J E0Y cos AX minus omega T plus epsilon. Okay, so what is epsilon over here? Epsilon is equal to the relative phase difference between the waves. Okay, both of which are traveling in Z direction. All right, so that is what you have. So in this particular case, if you look at it, so these are two waves which are at different phases, maybe relative phase between the two, and these are across different axes. So the resultant optical disturbance is therefore given as E z comma t is equal to Ex z t plus Y z. So if epsilon is equal to 0 or integral multiple of plus minus 2 pi, okay, the waves are in phase. Okay, in that case, okay, z comma t equal to I Ux plus j Uy cos a z. All right. Okay. This particular case, then this is what it becomes. So obviously the resultant wave, so this resultant wave is also linearly polarized. Okay, and the resultant electric field oscillates along a tilted line. Okay, so that is what you get at the end of the day. Okay, so in other words, if we have to put this pictorially, if we have to put this on pictorially, so let's try to do this. So you have basically, if you look at it, this is the Ey x, and this is the your resultant E, right? Okay. So there can be different combinations, larger and smaller, for example, and can have different directions of this light, okay, of this field. This is, and depending on the angles, depending on the strength, it can vary according to that. So this is a line along which the resultant E actually oscillates. Okay, so you can also have what we call circular polarization now. Circular polarization. What does circular polarization do? You can have another particular case where x equal to your E O y equal to E naught. Okay. In addition, okay, you have epsilon is equal to minus pi by 2 plus 2m pi, where m is equal to 0 plus minus 1 plus minus 2 da da da. So you can see that Ex z comma t equal to I E naught, okay, cos az minus omega t Okay. And your EY equal to Z comma T equal to J E naught cos KZ minus omega. Okay. So the resultant wave given as E naught I KZ E plus J I KZ. Okay. So this is what you are going to get, the two resultant. Okay. So the resultant wave is given by this. So this is what we call the right circular light. Okay. So this is circular polarization. So the resultant electric field E is therefore rotating clockwise at an angular frequency omega. Okay. Therefore, this is called right circularly polarized. So a linear polarized wave can be synthesized from two oppositely polarized circular wave of equal amplitude. So this is another thing that one should note, that a linearly polarized wave can be synthesized from two oppositely polarized circular waves of equal amplitude. Okay. So it essentially, therefore, you know, so that is what you get. Let one thing. So this is the important part, that it can be synthesized from two oppositely polarized circular waves of equal amplitude. So lastly, you have this elliptical polarization. Okay. We consider a general case. Recall general case, say for example, is EX is equal to EOX cos KZ omega T. Okay. And then you have EY equal to E naught Y into cos KZ ln. So expand the expression of EY. So if you expand the expression for EY into EY by E0Y equal to, okay, EY divided by E0Y is equal to cos KZ minus omega T cos epsilon minus sine KZ minus omega T multiplied by sine epsilon. Okay. Then if you also write EX by E0X equal to cos KZ minus omega T. All right. Okay. If you combine these two things together, so therefore it will be e y e 0y minus ex in e0x to cos epsilon equal to minus sine kz minus omega t, kz minus omega t sine. All right, okay, sine epsilon. So now we can say from this particular, if you look carefully, look at this particular equation, now you can say that, sine kz minus omega t equal to 1 minus x by 0x square raised to the power of half. Okay, what you are going to get. Okay, this also leads to, if you look at this expression now, okay, this also leads to ey 0y minus ex e0x cos epsilon square equal to 1 minus ex 0x square multiplied by sine square epsilon. Okay. So finally, if we rearrange all the terms, so finally we get ey by e0y square plus ex by e0x square minus 2 ex by e0x to ey by e0y cos epsilon equal to sine square epsilon. Okay, this is the equation. This is the equation of an ellipse. Ellipse making an angle alpha with ex, ey coordinates. Okay, so the tan 2 alpha is given as 2 e 0x e0y cos epsilon divided by e 0x squared minus 0y squared, right? In other words, this is like this. If I try to draw it properly, maybe I should. So these are the ex, ey, right? And, this is like a e0y x. Consider a box around it. Down a bit. Closes here. Okay. And this particular ellipse is something like this. Okay. So this is the E, and this is the major, this is the minor ellipse. This is alpha, okay, and this is E. Alpha, the axis of the ellipse. Okay, so if alpha is equal to 0, okay, epsilon is equal to plus minus pi by 2, plus minus 3 pi by 2. Okay, we will have this very familiar form, ey by E0y square plus x by E0x square equal to 1. Okay. Furthermore, if your EOY is equal to your EOX equal to E naught, so therefore this can be reduced to y square plus EX square is equal to E square. Okay, so clearly this is a circle. Okay, so if epsilon is an even multiplier okay, of pi, okay, then this results in EY is equal to E0y divided by EOX in EX. And for odd multiples, this is equal to EY minus E0y by E0x into EX, odd multiple. Okay, so these are both straight lines having slopes of plus minus E0y by E0x, and otherwise we have linear light. So both for linear and circular light may be considered to be special cases of elliptically polarized light. All right. So both of this, linear and circular lights, okay, are special cases of elliptical polarized light. Okay. So there are different configurations, different types of ellipses that you can actually have. So you can have those kind of configurations as well. So that is given. So, but you should also see that, in this particular example, sorry, that we mentioned, these are both straight lines. Their slopes are plus minus E0y by E0x. Okay, so that's why we know that there are linear and circular lights in general. So so this is in a nutshell what the ellipse is going to be, and what the ellipse is, how how the polarization actually happens. So basically it is given by the orientation of the final vector E over here. Polarization important component when we are dealing with light. Okay. Similarly, you can, you have wave propagation at an interface, then you have the Fresnel equations and lots of things that you are going to see in the next few lectures. But this is particularly important when we are talking about polarization. So polarization is basically, a plane wave which is propagating in the z direction can have two field components perpendicular to the propagation. As a result of that, you have that, and when you actually it is interpreted therefore as a sum of the two independent waves, which is Ex and Ey, and then what you get at the end of the day is a polarization which is given by the orientation of the vector E. And then of course there is this relative angle between the two. That means the relative phase between the two. So when the phase is basically 0, then the two waves are in phase, or if they are integral multiples of plus minus 2 pi. So so we have looked at circular polarization, we have looked at linear polarization, and we have looked at elliptical polarization, and we showed that why elliptical polarization is the key thing over here. That means all are special cases of that, how things can be determined from the electrical from the elliptical polarization. So in the next the class, we are going to look at therefore on wave propagation at an interface. That is the other important stuff. and that wave propagation at the interface, and then look at Fresnel equations, and then look at Fresnel equations in details, and then look at first order, second order, third order refraction points, the refraction modes, stuff like that. So, and then finally going on to scattering. So these are important things, and these are important, especially looking in when you have to look at light propagation and scattering. So light is an electromagnetic wave, which we showed, and therefore we need to know coherence, polarization, Snell's law, Fresnel equations, and Lorentz mean theory, geometric optics, and scattering from small particles before we go to the image processing fundamentals and end this particular section.